So if you see this, now we have to see how to find out the partial molar properties. So determination of partial molar properties, there are two methods. Both are graphical methods. Uh, one is tangent method, in which we plot total volume of the mixture or solution versus number of moles of second component. So if it is ethanol, water, it will be water, or if it is other way around, water will be ethanol. So we plot what is the solution volume by changing composition of the mixture and find out what is the volume of the mixture or solution, and plot volume of the solution versus number of moles of second component. So you'll get some curve like this. It may be like this, it may be some other shape also, doesn't matter. And this is always at constant temperature and constant pressure. So if you want the property partial molar volume at this value of composition, so we draw a tangent to the curve at that point. Right? The slope of the tangent is delta Vt, which is the total volume, divided by delta N2 at constant temperature, constant pressure, and constant N1. We are not changing N1, we are just saying that N2 is going to change because it's taking the derivative with respect to N2. And that is nothing but, by definition, partial molar volume of second component. Similarly, if you have to find out partial molar volume at this composition, draw the tangent at that composition, take the slope of the tangent, that will give us V2 bar. Any doubts, questions? Is it clear to all? Siddhi?
Sir, can you repeat?
Okay, so if you have to find the partial molar volume, not basically make a mixture of component 1 and component 2 are different compositions by changing number of moles of N1 and 2. So you get different composition, and plot total volume of the solution versus number of moles of second component. So you get some curve. Here it is shown like this, sloping downward. It can be anything. So if you want to find the composition or volume at any composition, draw a tangent to the curve by drawing a tangent to this curve at that point, at that composition. Slope of the tangent is Vt by N2 at constant temperature, pressure, and N1, which is by definition partial molar volume of second component. Is it clear?
Yes, sir.
Okay. This is the first method, but it's not very popular because it doesn't give very accurate results. So we look at the second method, which is called tangent intercept method. So similar to what you saw the first one, again we plot the total volume or molar volume of the solution versus x2, that is mole fraction of second component on the x-axis, and we get some curve like this. If you want the partial molar volume at, say, this composition, then we draw a tangent to the curve at that point. It will intersect this side at x2 equal to 0, 1 equal to, at x2 equal to 1 at point B. It will intersect at x2 equal to 0 at point A. Okay. So if you see this, if you draw a horizontal line at point P, So that is nothing but V, capital V, which is nothing but molar volume of the solution from here. That is F and F to C. Fc is nothing but molar volume of the solution, right? And AC, where the tangent intercepts the x-axis or y-axis at x2 equal to 0, is V1 bar. We'll see why it is V1 bar. Derivation we'll see. And the value from B to D on the y-axis at x2 equal to 1 is V2 bar. This is the derivation. And the slope of this tangent is nothing but delta V, molar volume by delta x2. Okay, so let's see the derivation. If we take a binary solution, we have n1 moles of 1, n2 moles of n2, component 2. Vt is total volume, and capital V is molar volume of the solution. This is the molar volume, capital V. So Vt is nothing but n, total number of moles, into molar volume. And total number of moles is nothing but n1 plus n2, component 1 moles plus component 2 moles, into molar volume. So that will give us total volume of the solution. So now we differentiate this equation 1 with respect to n1 by keeping temperature, pressure constant, and also n2 equal to constant. So what we'll get is delta Vt by delta n1 at constant temperature, constant pressure, and constant n2. And that is nothing but, by definition, V1 bar. So if we take the derivative of this side, we get, because we're taking derivative with respect to n1. So first term, so V into derivative of n1 plus n2 is 1, plus second term n1 plus n2 into derivative of V with respect to n1. So delta V by delta n1 at constant n2. Is this okay? Any doubts on this much? Any questions on what this first step we have done? By definition, we are taking what is total volume, is the number of moles into molar volume. And now we are taking derivative of total volume with respect to component 1 by keeping component 2 constant and temperature pressure constant. So this is a derivative which we derive by first, it's a product, right? N1 plus N2 into V. So first term into derivative of second plus second term into derivative of first.
सर हेलो
Yes.
सर तुम जरा फिर से दिखाए ना इसका
हाँ?
इसका डायग्राम ग्राफ फिर से दिखाए
डायग्राम बाद में वापस आएंगे, अभी डेरिवेशन करते हैं, बिकॉज यू विल अंडरस्टैंड द डायग्राम बेटर आफ्टर द डेरिवेशन. Okay, diagram I showed you before, but to understand that why it is V1 bar and why it is V2 bar, we have to see the derivation. That's why I don't want to focus too much on the diagram first. We'll do the derivation, then we'll see why this y-axis value at x2 equal to 1 is V2 bar, and why the y-axis value at x2 equal to 0 is V1 bar. That we'll understand only after the derivation. Okay. So if you have any questions on this derivative, ask me question. Then we'll come back to the diagram after the derivation is completed. Is this okay? Equation 2? Clear?
Yes, sir.
Yes, sir.
Okay.
Yes,
So
sir.
now we can define mole fraction. X2 is nothing but number of moles of second component divided by total moles, right? So N2 upon N1 plus N2. Now we differentiate this equation 3 with respect to N1 by keeping N2 equal to constant. So it's nothing but derivative of U by V, which is equal to denominator into derivative of numerator minus numerator into derivative of denominator divided by denominator square. This is what you've done in maths, right? So if you take dou by x2 by dou by n1 by keeping n2 constant. What you get is the denominator is n1 plus n2 into derivative of numerator dou by n2 by dou by n1. But by keeping n2 constant, right? So that's going to be 0. This derivative is going to be 0. Minus derivative of numerator is n2 into derivative of denominator dou by n1 of n1 plus n2 divided by denominator square. Is this okay? Is it clear?
Yes, sir.
Okay. So what we'll get is this term becomes 0 first term. So what you get is minus n2, and this, if we take derivative of n1 plus n2 with respect to n1, keeping n2 constant, what you get is 1. So n2 constant है तो 0 हो जाएगा ये derivative of n2 with respect to n1 like this one, and इसका 1 हो जाएगा. What it is minus n upon n1 plus n2 whole square. Is this clear? Any doubts on this derivative?
No, sir.
So this you can write as minus n2 upon n1 plus n2 into 1 upon n1 plus n2 because you want to convert this into fraction. So n2 upon n1 plus n2 is x2 divided by n1 plus n2.
Jenna. Hmm.
If you don't want to talk, don't want to speak, say something, please keep yourself muted. You can unmute when you want to talk. What you get is dou by x2 by dou by n1 at constant n2 is nothing but minus x2 upon n1 plus n2. Or we can take this on this side. We want to substitute here in this equation. So we take the terms on this side. What you get is n1 plus n2 upon dou by n1 is equal to minus x2 upon dou by x2. So we want to replace this term on the equation number which was given above, equation number 2. Okay. So we want to replace this term n1 plus n2 upon dou by n1, and that is equal to minus x2 upon dou by x2. This term will replace in the other equation by this term. So substituting in equation 2, what we'll get is we have taken dou by Vt by dou by n1 at constant temperature, pressure, and n2, right? And V was there, plus it was n1 plus n2 upon into dou by V by dou by n1. So we replace this term by this term, and we get minus x2 upon into dou by V by dou by x2.
Sir, could you please show equation 2 once?
Equation
2.
Yeah, this is equation 2. So we have dou by Vt by dou by n1 at constant temperature, pressure, and constant n2 is equal to V plus n1 into n2 dou by V by dou by n1 at constant n2. So what we are doing is replacing n1 plus n2 upon dou by n1 by minus x2 upon
What about 2?
dou by x1. Dou by x1 or x2? Dou by x2. We are replacing this term by minus x2 upon dou by x2. So what we'll get is this term was there on the left hand side, which is nothing but V1 bar, partial molar volume of 1. V was there, it was plus plus n1 plus n2 into double v bar double n1. So it becomes minus x2 into double v, which was there in the numerator, divided by double x2. Is equation 5 clear?
Yes, sir.
Okay. So let's proceed to now v2 bar. Then we'll come and correlate this equation 5 with the diagram and see how it gives that y-intercept. Okay. So for binary solution, we know x1 plus x2 equal to 1. So dx1 plus dx2 equal to 0. That means dx1 is equal to minus dx2. Now substituting this equation 7 in 6, what we'll get is, sorry, yeah, similarly like that, okay. Like we have derived this one, v1 bar is equal to v minus x2 double v bar double x2. We can similarly derive for v2 bar. We get the similar equation. And what we'll get is v2 bar is equal to v minus, instead of x2 it will be x1 double v bar double x1 instead of x2. So we have to replace x2 by x1 to get the equation for v2 bar. Just similar. This equation for v1 bar is v minus x2 double v bar double x2. So v2 bar will be v minus x1 double v bar double x1. Along the same line, we can do a derivation for v2 bar. Okay. So now what we'll do is we'll replace this double by x1 by double x2. dx1 is equal to minus dx2. So what we get is v2 bar is equal to v plus, it will come because this dx1 is equal to minus dx2 plus x1 into double v bar double x2. Because we have plotted x2 on the x-axis, so we want v2 bar in terms of x2, not x1. That's why we converted this equation to equation 8. Any questions, doubts on equation 8? No doubts, no questions? Okay. So let's see how we can correlate this with our, what do you call the graph. If you look at the graph, BD is equal to BE plus ED. Let's see. BD is equal to BE plus ED, right? If you look at this graph, this y-axis BD is equal to BE plus ED. And if you take the slope of this tangent, slope is perpendicular upon base. So it is BE upon PE. So BD is equal to BE plus E, slope is equal to BE upon PE, that is perpendicular upon base. So B is nothing but slope into PE, right? And slope is nothing but double VT by double X2, right? That's what we have plotted, right? VT versus X2. Slope is double VT by double X2. And PE, what is PE? PE is nothing but, this is x2, this is 0, so it is 1 minus x2. PE, this distance is 1 minus x2, because 0 to 1. Okay, is it clear?
नो सर, नहीं समझा
क्या नहीं समझा?
सर। वो 1 माइनस x2 कैसे आया? वो
x-axis is 0 to 1. This is mole fraction, right? Mole fraction is always between 0 and 1. बराबर? So यहाँ पर x2 वैल्यू है, यहाँ पर 1 वैल्यू है, तो ये डिस्टेंस, ये जो डिस्टेंस है कितना होगा? ये x2 से 1 तक कितना डिस्टेंस होगा? What is the value? यहाँ से यहाँ तक x2 है, right? If it's suppose say 0.4, so this is 0, this is 0.4, ये 1 है, ये distance कितना होगा? अरे भाई ये पूरा एक्सेस 0 to 1 है, right? Distance from here to here, from C to D is 1. C to x2 is say 0.4. So x2 to D कितना होगा?
Yes, sir.
0.6.
Minus x2, right?
0.6.
0.6.
0.6.
So if this is 0.4, this will be 0.6. So D minus x2. That's what we are saying here.
Okay, sir. Got it.
1 minus x2. Right? So B is nothing but this derivative or slope into 1 minus x2. And what is ED equal to? ED is nothing but this molar volume, right? ये देखा था. ED is FC, is molar volume of this solution, right? At this point. So what we get is BD is equal to B is nothing but V plus ED is sorry, B is 1 minus x2 into double Vt bar double x2, which is nothing but V2 bar. We have seen that equation for V2 bar is V plus 1 minus x2 double Vt bar double x2. समझा? कितने लोग को नहीं समझा?
सर सर वो ईडी है
समझा
ना
क्या?
सर ईडी है ना वो टोटल मोलर वॉल्यूम कितना है ईडी इक्वल टू वी
It is total molar volume because the y-axis का क्या वैल्यू है उसमें?
नहीं सर वो टोटल
Look at this
मोलर
y-axis. Total molar volume, है ना? Because you are plotting total molar volume versus x2. If I take any point on this curve, y-axis is total molar volume for that composition. Okay, let me do something else. Can you see this paint? Are you able to see?
Yes, sir.
Yes, sir.
बहुत ही कहा रहा है क्योंकि मैंने बहुत जूम कर लिया. Okay, so if I take a tangent, ठीक है? So I draw a tangent, and what I am saying is, so this is point A, this point C, and this is B, this is D, and I draw horizontal line from here. This is F, this is E, this is P. Thick हो गया ये lines. How do I change the lines? So we have this total molar volume, or molar volume, not total molar volume, it is molar volume. And this is X2. Okay, so if I draw a tangent here, and this horizontal line is V. Okay, so what we have is B is equal to B, BD is equal to B plus CD, right? And what is B equal to? If we take the slope of this angle, it is BE upon PE. Okay? Perpendicular upon base. So B is equal to nothing but slope into PE. And slope is over T divided by X2 at constant temperature, pressure, and N1 into PE. What is PE equal to? P is equal to 1 minus X2. This is 1. And this is 0. 1 minus X2 plus ED. ED is this short value is nothing but V. Right? दिख रहा है क्या आप लोगों को? Can you guys see?
Yes, sir.
Yes, sir.
Can you see?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So BD is, then what is BD? BD is nothing but, then what is BD equal to? V2 bar, right? This is what by derivation we said, V plus 1 minus X2 into double VT by double X2. So is it clear now? कोई डाउट है अभी किसी को इसमें?
So, but that's BE is equal to V2 bar, right? In the original diagram, it was BD is equal to V2 bar.
क्या बोले?
In this diagram, according to the calculation we've done, we get slope is equal to B upon D.
Yeah.
Yeah. So that becomes BE is equal to, no, just a
Slope
minute.
into P, you know. B is
Yeah.
equal to slope into P.
Okay, so BE will be equal to V2 bar, right?
Yeah, that's what I added, no? First I've added BE. BE is equal to 1 minus X2 into double VT by double X2. And ED is nothing but V plus V.
Okay. Okay, yes, I get it. Yeah.
ठीक है? Similarly,
Yeah,
we
yeah,
can do
yes.
for V1 bar. If we take the slope on this side, we take the slope on this side, what is it? AF upon PF. Right? If if you take the slope on this side, it is AF, this is the perpendicular, and base is PF. Right? Correct? So AF is equal to slope into PF. And what is slope? Slope is double VT upon double x2 into PF. PF is what? PF is nothing but this into this, that means x2. Okay? So you know what is AF now? AF is nothing but double VT by double x2 into x2. And now we can write AC. This is what we want, right? AC is equal to AC is nothing but FC, this total distance, minus AF. And what is FC? FC is nothing but capital V. This is what we said, right? This is FC, capital V. So what we get is capital V minus x2 into double VT by double x2. This is nothing but V1 bar by definition. The derivation which we have done. Okay. Any doubts, questions on this so far? The derivation you have seen, you understood. Now we are just trying to correlate derivation with the diagram. So it will tell us that okay, this thing is V2 bar and this value is V1 bar. I don't know why the lines are coming so bad. I'll do something, work on it. But you understand now what is V2 bar and V1 bar. From diagram we can get it. If you take the tangent at any point, intercept at x2 equal to 1, this is V2 bar, and intercept at x2 equal to 0, this is V1 bar. This method is more accurate because now we are using the slope value as well as the intercept value. We are not just using the intercept slope value like in the previous method. Any doubts so far?
Sir.
Okay, so then that completes a partial molar properties topic. Then we'll move on to second topic, next topic, which is chemical potential. Okay. So you have seen lead heat transfer, right? Heat transfer किया है आप लोगों ने? Hello. Hello. Somebody has to answer.
Yes, sir.
Heat transfer. So what is the driving force for heat transfer? Is there a driving force there in heat transfer? How does heat transfer take place?
Yes, sir.
Temperature difference.
Temperature difference.
So if there is a temperature difference, then only heat transfer will take place, right? Correct?
Yes, sir.
Fluid flow
Yes,
किया
Yes,
आप लोगों ने?
sir.
Fluid flow किया कि नहीं? You done fluid flow or not?
Yes, sir.
Hello?
किया ना.
Yes, sir.
So how does
Yes,
flow or how does the fluid flow?
Pressure gradient, sir.
Pressure gradient. If there's a pressure difference only, then what fluid will flow, right? Like if we are living in a society, the overhead tank is at higher level, the potential energy is more. That is why the water comes down by gravity to your home. The pressure difference drives the flow. So now, for chemical equilibria and for fluid phase equilibria, we have defined a similar concept, which is called chemical potential. So chemical potential is index of chemical equilibrium. Just like temperature is index of thermal equilibrium and pressure is the index of mechanical equilibrium. So for fluid flow, we need pressure difference. For heat transfer, we need some temperature difference. Similarly, we need some chemical potential difference for reaction to take place and for phase equilibrium. So that's how we define this chemical potential. The chemical potential is defined as mu I, mu subscript I for component I is equal to partial molar Gibbs free energy. That's why we've seen partial molar properties, right? Basic objective was to understand what are partial molar properties and then define chemical potential, which is nothing but partial molar Gibbs free energy. Why Gibbs free energy? Why are we using Gibbs free energy? Why not Helmholtz energy? We have seen A and G, right? Gibbs free energy and Helmholtz energy. What is the difference between A and G?
Gibbs free energy is asking that ideal gas is constant temperature and pressure. Gibbs free is achieved at
If you're not talking, please mute yourself. I don't want to hear what is in the background for you. You unmute yourself only when you are talking. Why are we using Gibbs free energy, not Helmholtz energy?
Sir, because it is at constant temperature and pressure.
Yes, because it is constant temperature and pressure, and that is what is most relevant for all chemical processes. And that shows us what is the net work available, right? Helmholtz energy gives total energy, total work available, total available work, but Gibbs free energy gives us what is the net work available for use in our processes. That's why we are defining it based on Gibbs free energy. Okay, so mu subscript I is equal to Gibbs free energy I bar, that is partial molar Gibbs free energy, and that is nothing but dou GT by dou Ni at constant temperature, pressure, and constant N subscript J, where J is not equal to I. This is a definition of partial molar property. That's how we define total derivative of total property with respect to the component. Okay, so that's our definition of partial molar Gibbs free energy or chemical potential. This is you should remember. Now I take total free energy of a solution, G superscript T. It's a function of temperature, pressure, and number of moles of all the components. And if you take the total derivative of this total Gibbs free energy, dGT, equal to dou GT by dou T at constant pressure and number of moles of all components into dt plus dou GT by dou P at constant temperature, number of moles, total moles into dP, plus if you have N1, N2, N3 up to Ni, then summation of dou GT by dou Ni at constant temperature, pressure, N subscript J, where J is not equal to I, into dNi. Because we can take all this, which is N1, N2, N3, and sum it up. So this is our total derivative. Okay. So this becomes, by definition, this is nothing but mu I, dou GT by dou Ni. This is what we defined here, right? This is the same thing. So we can replace this with mu I, and what we get is dGT is equal to dou GT by dou T at constant pressure, number of moles into dt, plus dou GT by dou P at constant temperature, number of moles into dP, plus summation of mu I into dNi. Any questions on this equation? Can you hear me?
Sir.
Hello.
Sir.
Yes, sir.
So is there any question or doubt on this one?
Sir.
सर वो UI क्या लिया है लास्ट में इक्वेशन 1 में?
म्यू आई है, म्यू आई डिफाइन किया ना यहाँ पर म्यू आई. You defined already mu I. Mu I is nothing but partial molar Gibbs free energy. Dava GT by dava Ni at constant temperature pressure n subscript j, j is not equal to 1, I not equal to I. यहाँ पर भी वही है. This term is same. This is the definition of mu I. यहाँ पर जो define किया है. We are just substituting this term by mu I. This term is replaced with mu I.
ओके सर, आया समझ में.
Okay. So, for closed system, dg is equal to vdp minus sdt. We have done this already derivation. So if you write for total properties, dgt is equal to vt into dp minus s superscript t into dt. And if you take a derivative, or rather we take it at constant pressure, dp becomes 0. What you get is dava gt by dava t at constant pressure n is equal to minus st. And at constant temperature, what you get is dava gt by dava p at constant temperature n is equal to vt from this equation. Okay. So now you know this is minus st, this is equal to vt, and this is what we have there, right? Dava gt by dava t at constant pressure n, dava gt by dava t at constant temperature n. So we can replace these two terms, and what we'll get is dgt is equal to, this is the first term, vt into dp minus st into dt plus summation of mu I dni. Any questions on this equation 4? किसी कोई डाउट है, क्वेश्चन है? No response. Somebody has to respond, right, when I ask a question?
No doubt, sir. No doubts.
Okay. So in that case, we have this equation, and it is called fundamental relationship for changes in free energy of solution. We have seen fundamental relations before also, right? देखा कि नहीं? That was
sir,
for
देखा, sir.
Yes,
that
sir.
was for closed systems. Now this is involving chemical equilibrium, fluid phase equilibrium. So if you have phase equilibrium, पहले था dg equal to vdp minus sdt, right? ये था ना आपका पहला. What we had derived before was dg equal to vdp minus sdt for a closed system. बराबर ना? ये यहीं पर है. This we had derived. But now because of chemical equilibrium or fluid phase equilibrium, we have to add this term on the right hand side, and that is our fundamental relationship for changes in Gibbs free energy of solution. And if you have at constant temperature and pressure, dp becomes 0, dt becomes 0. So dgt at constant temperature pressure is nothing but summation of mu I dni. Any doubts on this? Because we are going to use this continuously. This is our starting point for all phase equilibria and chemical equilibria. Okay, if there is no doubt, then we can proceed further. So dgt is, you can write the summation as mu1 dn1 plus mu2 dn2 up to an I component, or we can write as mu I xi, mu1 x1 plus mu2 x2 plus mu I xi into dn. So we are writing dn1 is equal to x1 into dn, dn2 equal to x2 into dn, etc. So we can take out dn common, and what we get is, if we integrate this equation 5, we get gt on the left hand side, and then we get mu1 x1 plus mu2 x2 into n, because dn will become n, or we can also write as mu1 n1 plus mu2 n2 up to I component. So this total free energy is nothing but sum of partial molar chemical potential of constituents weighted according to its number of moles. So mu1 into n1, mu2 into n2, etc. for all components. Or we can write as Gt is equal to summation of mu I into Ni. Okay, any doubts, questions on this?
So could you please scroll up for a minute?
This is mu1 x1 plus mu2 x2. Okay. So what we get is Gt is equal to summation of mu I Ni, and for 1 mole of solution we get Gt is equal to summation of mu I Xi, because n total n is equal to 1. So we have two equations now. Gt is equal to summation of mu I Xi, or dgt is equal to summation of mu I dxi. We had done similar thing for partial molar properties, right? Remember last week? The derivation is similar.
Yes, sir.
For partial molar properties also we have done the similar things, similar derivation. The thing is now it is chemical potential. Okay. So for binary system it will be G equal to mu1 x1 plus mu2 x2. We had done for molar volume, V is equal to V1 bar x1 plus V2 bar x2, right? And we solved a problem also on that. So this, if you take that equation, we can directly actually use this thing, because mu1 is nothing but partial molar gives free energy, and mu2 is nothing but again partial molar gives free energy. So that equation can directly be used, but we have done the derivation here. So chemical potential of a component is the contribution of that component to Gibbs free energy of solution, right? So we are saying, as you said, partial molar volume was nothing but partial component contribution of component 1 to volume of the solution. Now this is contribution of component 1 to Gibbs free energy of solution, right? Because this G is Gibbs free energy of a solution, right? So chemical potential is important property of solution used in study of phase equilibrium and chemical potential, chemical equilibrium. So we are going to talk about this in unit 1, 2, 3, 4 phase equilibrium and 5, 6 for chemical equilibrium, and we will be using mu I throughout. So you understand chemical potential now. It's nothing but partial molar Gibbs free energy of a component.
सर एक डाउट था
बोलो.
सर, वो फिर अगर हमने वो टोटल प्रॉपर्टीज की रिलेशन देखा तो समेशन म्यू आई डी एन आई 0 आना चाहिए ना, अगर हमने वो एनालॉगस लिया तो.
No, because see, first when we considered that other thing, we didn't consider chemical equilibrium and phase equilibrium. Now, because we are considering this phase equilibrium and chemical equilibrium, we have to add that thing. Zero नहीं होगा वो. See, that previously what we did was not considering phase equilibrium and chemical equilibrium. So that time it was different. That's why it was dg equal to vdp minus sdt, right? Now when you involve chemical equilibrium or phase equilibrium, another term has to come in to represent what is that phase equilibrium and chemical equilibrium, and that is why the summation of mu I d and I is there. तो 0 कर दिया तो mu I 0 हो जाएगा ना, because Ni cannot be 0.
सर क्योंकि हमने वो जो है वो सब्स्टिट्यूट कर दिया ना, डेबा जी बाय डेबा टी को माइनस एस सब्स्टिट्यूट कर दिया, डेबा जी बाय डेबा पी को वीटी सब्स्टिट्यूट कर दिया।
It is using the previous equation, but now we are accounting for chemical equilibrium, phase equilibrium. अगर जीरो कर दिया तो then there is nothing. You can't do anything. phase equilibrium में कुछ नहीं आएगा. इसको जीरो ही कर दिया तो क्या करोगे? इसको अगर जीरो कर दिया तो ये जीरो हो जाएगा. Then what are you going to do in chemical equilibrium, phase equilibrium? Because previous thing जो हमने derive किया था VdP minus SdT, that was for involving non-equilibria, non-phase equilibria, non-chemical equilibria. Right? It was considering only, say, volume solutions, not involving equilibria. Now we are involving equilibria, so we have to account for the equilibrium also, and this is what is accounting for equilibrium. If there is no chemical equilibrium, then yes, this is applicable. If there is no phase equilibrium, then this term is not involved. If there is no chemical equilibrium, then this term is not involved. Then it reduces to our old equation. D is equal to VdP minus SdT. But now because equilibrium is involved, we have to account for that. That also contributes to this energy of the system. ठीक है? Any doubts, questions so far? So we'll continue from here tomorrow. I'll put this notes on the Teams folder. You can go through it because understanding this concept is important for all units up to phase equilibrium and chemical equilibrium. It is the basis for all our derivations and everything. ठीक है?
Yes, sir.
ठीक है. I'll stop the recording and then we'll end the meeting. Okay, see you tomorrow.
Thank you.